Okay, assignment 13, question 1. Up until now, the force of gravity was calculated using this equation. You would take the mass of the object and multiply it by g, which we were using 9.80 meters per second squared. However, now we're going to think of g in a new way rather than the acceleration caused by gravity at the surface of the Earth. We're going to think of it as the strength of gravity or the strength of the gravitational field at the surface of the Earth. And so we'll use another set of units, which end up being the same units, 9.8 newtons per kilogram. So it means at the surface of the Earth, every kilogram of mass will give you a force of 9.8 newtons. So 1 kilogram, 9.8 newtons, 2 kilograms, 19.6 newtons, and 10 kilograms, 98 newtons. However, we didn't discuss, but you should realize that if you leave the surface of the Earth, that this g is going to be different. So maybe you've heard that the acceleration due to gravity or the strength of the gravitational field on the surface of the moon is only about 1/6 that the gravitational strength on the surface of the Earth. So anyway, Newton formed a more general law for the force of gravity that exists between any 2 point masses in the universe. And here it is. It's called Newton's law of universal gravitation. It holds true for any two objects that are either spherical or relatively small. So this works for point charges. And a sphere, like the Earth and the Moon, are far away from each other, so they're small relative to each other, so they're like point charges. So if we wanted to calculate the force of the Earth on the Moon, we would take the universal gravitational constant g, which has this value, and we would multiply it by the mass of the Earth times the mass of the Moon times the distance between their centers squared. So this is the form of the law, and it makes sense if you think about it. There's some constant that makes the units correct, and the force depends on the mass of each object and the distance between them. And it's squared because of the nature of space, which we'll describe later. So it's called an inverse square law. So if we can use this law in question 1 to calculate the quantities that are requested. You do have to be careful that you use the mass in kilograms and that the radius or the distance between the objects you're calculating it for are in meters. Okay, there's a solution to question 1, to the first part of question 1. So there's notice the formatting. Here's the general equation. Wrong G, I should have used the capital G, or I could have put FEM for the force between the Earth and the Moon. There's the gravitational constant. Oops, I forgot the 10 to the minus 11. But I did get the units there. And then there's the mass of the Earth. Those quantities are all given in the question. There's the mass of the Moon. That's the distance, but notice it's given in kilometers, so I changed it to meters from 5 to 8. And square it, and then you should get this answer. And notice the meters get squared, so those units cancel. And there's kilograms squared here, so that gets canceled. and so the units end up being newtons. Okay, I skipped the next problem, which is the force of the Earth on the Sun. One of the things I didn't mention on the previous one is the force of the Earth on the Moon and the force of the Moon on the Earth are equal and opposite, right? They're all the same numbers. And by Newton's third law, those two forces have to be equal and opposite. Of course, the Earth is so much more massive that its motion is not affected much by the Moon. But if you look closely, you'll see the Earth does wobble a little bit according to the force of the Moon on the Earth. Okay, so skipping ahead to the next one, here's the equation. We're calculating the force of the Earth on a person. So g, the mass of the Earth, the mass of the person, and the radius of the Earth, because the distance from the center of the Earth to the center of the person is the radius of the Earth. Those numbers are given, but notice how I rewrote this. I put the g and the me and the re squared all together, because now you can see that the force of the Earth on the person is this times the mass of the person. So if you calculated this alone, you'd see that it comes out to be approximately 9.80 newtons per kilogram. And that's because we're at the surface of the Earth. If we move away from the surface of the Earth, this will get smaller. So here are the numbers. Notice that you were given the diameter of the Earth, so I had to divide by 2, and I had to change it from kilometers to meters, so that's the number I get. And so if we were to just calculate this number, you'd see it comes out to about 9.8 newtons per kilogram times the mass of the person. This number will be different. This number is not the same for all of you, but I was using 60 kilograms. So if you do this, you will get the answer. Okay, the last problem in question 1 is just using this again, only in this case, we'll see a problem later about this. There's a rod with 2 small masses that's free to rotate, and then there are 2 larger spheres that are placed close to the smaller spheres that are fixed, and so there'll be a force between these 2 balls that will make this one rotate this way because it's free to move, and that one rotate that way. So in this problem, we're just calculating the force between these 2 masses. So we use the distance between the centers of the 2 masses, it has to be in meters. We use the mass of the 2 masses, has to be in kilograms, and then we use our gravitational constant. So just make sure you get all the units right, and no surprise, this will be a very, very small force because the gravitational attraction between 2 objects that aren't massive like the Earth or the Moon is going to be very small. Okay, we're moving on to question 2. We're going to continue to use the law of universal gravitation. We'll also use Newton's second law, which relates net force to mass and acceleration. And since objects moving in a circle are subject to a centripetal acceleration, we'll use either of these equations for centripetal acceleration, right? An object moving in a circle at a constant speed is subject to an acceleration towards the center of the circle, which can be calculated using the tangential velocity divided by the radius, or the angular velocity squared times the radius. So here's the Earth and here's the Moon, and the Moon, of course, is going around, but they're both pulling on each other. And so, we're assuming that the only force acting on the Moon is the force of the Earth, and use this equation to write the forces acting on the moon equal to its acceleration. In other words, combine these two equations and write the equation for the moon. Try to do that yourself. So here's the free body diagram. I'm using this equation. The sum of the forces acting on the moon is this force, right? The force of gravity. And it should be equal to the mass of the moon times the acceleration of the moon. Now notice the mass of the moon is on both sides of the equation. So I can cancel that and then solve for the mass of the Earth. Do the algebra and come back. Okay, there's the equation you should have gotten. Let me just remind you that the distance between the Earth and the moon is what goes in this equation. Here, this is the omega times the radius of the circle. So the radius of the circle that the moon moves in is that same REM. That's why these are the same. And then when we do the algebra, we get this equation. And so we know G. We need to know or measure or be told the distance from the Earth to the moon. And then omega is the rate at which the moon is going around the Earth. So that's going to be 2 pi radians in the period that it takes to go around. And so the problem gives you that. It's 27.3 days for the moon to move 360 degrees around the Earth. And so now you just got to put the numbers in and solve it. So omega is 1 cycle, 2 pi radians, 27.3 days. So you got to convert the days to seconds, right? So 27 point, remember how to do this, practice this. 27.3 days, 24 hours in 1 day, 3,600 seconds in 1 hour. And so that converts days to seconds. That number will go there, 2 pi on top. That number will go there. You'll square it. The radius or the distance from the Earth to the moon is given. You got to cube that. Make sure you use units of meters. And G, you know that number well. That goes there. And that will end up giving you the mass of the Earth. Okay, the same method can be used to get the mass of the sun, only in that case you'll have the mass of the sun, the mass of the Earth, the distance from the Earth to the sun, and then the mass of the Earth times omega for the Earth around the sun times that same distance. So it's going to be the same equation, only the omega will be the 365.24 days turned into seconds divided by into 2 pi. You'll square it, that distance, make sure it's in meters, and G should give you the mass of the sun. It's exactly the same method. Okay, now we want to talk about gravitational field. If we go back to our old equation for the force of gravity, it's the mass times G. But what we said earlier is G has a constant value at the surface of the Earth. But in other locations in space, if we let G change, then we can still use this equation. It's just the mass times the gravitational field strength. The strength of gravity at any location measured in newtons per kilogram. And so if we divide both sides by m, we get a definition for G, the gravitational field. And we're going to make it a vector equation because this force is a vector. And so this is our general definition of G. It's the force of gravity per unit mass for any point in space. And so the second mass divides out, and this becomes, for any point mass, the force of gravity due to any mass m at a distance r from the center of that mass to any point is what we define as g. So if we wanted to find g at the surface of the Earth, we'd use this equation. We'd put in g, the mass of the Earth, times the radius of the Earth, because it would be the distance from the center to here. But if we wanted to find g at a point some distance from the Earth, then we would use the same g, the mass of the Earth, but now the distance would be from the center of the Earth to this point, or the center of the Earth to this point. So we can use this equation to find the gravitational field strength at any point in space for any mass. This could be the moon, it could be the sun, it could be Jupiter, it could be any body, and we could find the gravitational field at any location from that body simply by using this equation. But once again, make sure that the mass is in kilograms, and the R that you're using is in meters, not kilometers or any other unit. And so the questions in question 3 can all be answered using this equation. Okay, let's discuss gravitational energy or gravitational potential energy. We're now using the symbol U rather than PE, so UG up until now has been MGH. Only now we know that G is a constant value only at the surface of the Earth. And remember, the way we think about gravitational potential energy is the work required to move a mass from a low place to a high place. So work is a force times a distance. The force is the gravitational force, and the distance for us was the height we lifted it to. But now we want to generalize this, and we want to calculate the work, say, that it would take to move an object, say a satellite, from the Earth's surface to some position far away from the surface. And so we're going to do the integration of the force of gravity times the displacement in small amounts integrated, right? So FG dx integrated between A and B. Let me write that in. So we're integrating from A to B. We're moving the satellite from point A to point B. And the force is the G, the mass of the Earth times the mass of the object, the satellite, divided by the distance squared, where XA is from the center of the Earth to point A, and XB is going to be from the center of the Earth to point B. And so when we integrate dx over x squared, we get x evaluated between A and B. So the change in gravitational potential energy from A to B is minus G MEM XB minus a negative G MEM XA. This will be the bigger number. The two negative signs cancel. Mathematically and physically, the change in gravitational potential energy has to be positive because it takes work to move the satellite from here to here. And so it has more gravitational potential energy in this position than it does in this position. And this is how you calculate it. Now, the reason that the physical reason, the mathematical reason comes out of the integration, but the physical reason that gravitational potential energy is a negative is because gravity is an attractive force. And so the energy, the number goes up, but it becomes more negative. And the zero energy, right? You don't get to the surface of the Earth and it's zero. So the zero energy is when the Earth and the object are separated by a far distance. So if you take this equation where x is very large, this becomes 0. So mathematically and physically, it makes sense to have all gravitational potential energies using this general equation to be negative numbers. The other question that comes up in the assignment is that if you throw a ball up, it comes back down. And if you throw it faster, it goes up higher and comes back down. And the faster you throw it, the higher it goes before it comes back down. And it doesn't depend on the mass of the object, right? No matter what I throw up at 30 meters per second, it's going to go up. It'll go up 45 meters and come back down. So the question that is of interest is, how fast do I have to throw it so that it has just enough velocity or energy to escape the hold of gravity, and it just has enough energy to get away. So that's an energy problem. That's a law of conservation of energy. So see if you could write down the equation that will allow you to find the velocity necessary for an object thrown to escape the gravity of the object, in this case the Earth, and never come back. So here's the conservation of energy equation. The change in kinetic energy has to be equal in magnitude to the change in gravitational potential energy. And K final will be 0, right? It's going to be thrown with a velocity, but if it gets far away, it doesn't need to have any velocity. It can just be 0. And the potential energy when it's far away is 0. So K initial has to be equal to the U initial, and K initial is 1/2 the mass of the object times the velocity of the object. We're calling it the escape velocity squared. That's the kinetic energy original, and it has to be equal to the potential energy, which is G, the mass of the Earth, the mass of the object, divided by the distance between them in the beginning. That's the radius of the Earth. So solve that for V escape. Okay, there's the solution. The escape velocity is simply 2 times g times the mass of the Earth divided by the radius of the Earth. And so you can imagine that this works for any object. This could be the mass of the moon and the radius of the moon. It could be the mass of the sun and the radius of the sun. It could be the mass of a black hole and the radius of a black hole. This would be the escape velocity for any astronomical object. And in fact, what makes a black hole black is that the escape velocity is the speed of light. So if we take this equation and put in the mass of a black hole, put in the velocity of light, and solve the equation for the radius of the black hole, we can get an idea of how big something with the mass of the sun or the mass of 3 suns would have to be to have a gravitational field that was strong enough to make the escape velocity equal to or greater than the speed of light. That's the last problem in this section. So we use the same equation for that too. So the next two problems are satellite problems. So a satellite has to have a certain speed to be in a stable orbit. There's a very well-defined speed, because if it's going a little bit slower, it's going to end up falling to the Earth. And if it's going a little bit faster, it'll spiral away from the Earth. And to get that, we take the satellite, and the only force, the dominant force acting on it, is the gravity force of the Earth pulling it down. But if it has the right velocity, it will move in a circle in a stable orbit. So we go to Newton's second law that says that the sum of the forces on the satellite have to equal the mass of the satellite times the acceleration of the satellite. So the force on the satellite is this, g times the mass of the Earth times the mass of the satellite times the distance from the Earth to the satellite. That means from the Earth to the surface plus the surface to the satellite. So you have to add those two numbers together. You have to make sure that the units are in meters. That force, that one force, which is the net force, is equal to the mass of the satellite times its centripetal acceleration. And since we want, in this case, we want the velocity, we'll use v squared over r. So, and that r is the radius of the circle, which is the same as the distance from the center of the Earth to the satellite. So solve this problem for v. That'll be the v that we need for the satellite to be in a stable orbit. So there you are. Mass of the satellite cancels. It doesn't depend on the mass of the satellite. And the velocity depends on g, it depends on the mass of the Earth, and it depends on the distance that you are from the Earth. So the further away from the Earth that you get, the bigger this number, the smaller the velocity has to be. And you could generalize this if you wanted to know the velocity of a satellite going around the moon. You would simply use the mass of the moon and the distance from the moon center to the satellite center. Or the velocity of the Earth going around the sun would be the mass of the sun, and the distance from the center of the sun to the Earth would give you the velocity at which the Earth is moving around the sun. So this is a general result. The second satellite problem is, what if we wanted a satellite that stayed over the same place on the Earth? In other words, it orbited the Earth with a period that exactly equaled a 360-degree rotation of the Earth, which, as explained in the problem, is a little bit less than 24 hours. And so in this case, we want to change the v squared r to omega squared r. So solve, and we want to find the period. We want to find the distance at which that synchronous orbit would take place. So write a similar equation using omega squared r and see if you can solve it. Okay, I hope you tried. So here's the force equal to the mass times the acceleration. The gravitational force equals the mass times the acceleration of the object, where we're using omega squared r. R is from the center of the Earth to the satellite. And this is the thing we're trying to find. At what distance will a satellite go around so that the period, or the length of time, is equal to the time for 360 degrees of rotation, which is this time. For reasons I'm not explaining, it's not exactly 24 hours. So the mass of the satellite cancels. We bring the r squared over here and we get r cubed. And then if we solve for this, then we have GME divided by omega squared, and then we take the cube root of that, and we'll get the distance. Again, what's omega? Omega is the satellite must go a full rotation, 2 pi radians, in 23.933 hours you need to convert that to seconds. Put it in there. You're going to have to square it, do all this math, take the cube root, and that should give you the distance of a geosynchronous satellite. Okay, here's the space station question. So if we have a donut-shaped spinning space station and it spins at just the right speed, it will be pushing all the objects toward the center with a centripetal acceleration that exactly equals, that will be either v squared over r or omega squared times r, should equal 9.80 meters per second squared, or newtons per kilogram. So all you're going to do is set, if you want the rate of rotation, set the omega squared r times the 9.80 meters per second squared and see what you get. And you can see that the rate at which it rotates will depend on r. So as r gets bigger, the rate of rotation will be smaller because it equals a constant 9.8. Go ahead, try it. So the rate of rotation will be the square root of g over r. That's your g value. So it depends only on r. Of course, that's going to be in radians per second. So if you wanted it in rotations per minute or some other unit, you have to convert the units. Okay, question 8, the Cavendish experiment. So you can see photographs, and hopefully you've seen the apparatus in the classroom. There's a long, thin thread that comes down to the center of a thin rod of negligible mass, and two relatively small tungsten spheres at the end of those rods. On a much bigger sphere on a base that is fixed but able to rotate is here, and this can rotate toward either side. So if we look at it from above, looking down, here's the rod, here's the two small masses, and here's the two big masses on this larger platform, and it can rotate either way. So when it's in this position, the forces between the small and the large sphere cancel, and there's no net force or net torque. But if we rotated this apparatus this way, so that the big ball were here and this big ball were here, then there would be a force of attraction on the small ball this way and a force of attraction on the small ball this way, and that would put a net torque twisting this thing that is free to move in this direction. And so in this problem, you're going to calculate first the force, like move this here, and that one moves here. And so there's a force this way and an equal force on this one this way. And that you just use the g, m of the 1, m of the 2, and the distance between their centers squared will give you the force. The torque, however, is the force times the r times the f times the sine of theta. So these forces are perpendicular to the rod, so we don't need to worry about the sine of theta. And the r, the torquing, that's the distance from the axis to where the force acts. So it's half the distance between the centers of the two balls. I think they give you the distance of the centers of the two balls. You got to divide that by 2, and you multiply it by the force. And since there's 2 forces, the total torque will be the sum of both torques, right? Because this force is torquing this clockwise, and the torque on this one is torquing this clockwise. So this is clockwise torque, which is double the individual torques. Then, I hope you recall, to get the acceleration, you have to take the net torque and divide it by the rotational inertia. And the inertia of the rod is considered negligible because the mass is so small compared to the mass of the balls. And so the inertia is simply the sum of m1 r1 squared plus m2 r2 squared, but m1 and m2 are the same, and r1 and r2 are the same. And so that will give you the inertia, and through that you can get the acceleration. The final question is to get how long it takes to turn. I'm going to do another drawing. Okay, let me see if I can explain this. If the laser is here and the beam comes straight in, it bounces straight back. Now, supposing this rotates 10 degrees, and the mirror now is this way. So now the mirror is facing this way. It's rotated 10 degrees, but now the beam is going to come in and hit the mirror at 10 degrees to the normal, and then go out at 10 degrees. So whatever the angle of rotation is, the angle between the laser beam is going to be double that. That's the tricky part of this. You have to picture the mirror, right? The mirror rotated 10 degrees, but now the beam comes in to the surface of the mirror, twisted 10 degrees. It bounces off the mirror and goes out. So it goes through a change of angle of 20 degrees. So if the laser beam moves 20 centimeters from, say, 4 meters away, then from that you can get the angle. This is small enough you can consider it an arc length, but you have to cut the angle. That's going to be double the angle that the mirror rotated. So the mirror rotated, right, the angle in radians is the S over the R. So rather than use the 20 centimeters, since the angle of rotation of the mirror is only half, so that'll be 10 centimeters or 0.1 meters divided by, I think I remember correctly, it was 4 meters. And so that's the angle of rotation of the mirror. And since we know the acceleration, we're going to use the equation that delta theta, we got to go back to our equation sheet, equals omega initial t plus 1/2 alpha t squared. But the apparatus started at 0, and it's asking us how long it will take to go through a rotation of that angle. So solve that for t. pause the video and do the algebra. T is going to be 2 times the change in angle divided by the acceleration that we found, dividing the torque by the inertia. We just talked about that. And that's how you're going to get the time. Okay, not easy. Good luck.